Oh well, welcome everybody. This is a big turnout. It is a little bit overwhelming standing up here, but that's great. We'll get used to it. So I guess welcome tonight. For those of you that don't know me, my name's Brett Henderson. I work with DigIO. So tonight, my colleague and I, Ben Ebsworth, we're going to, I guess, share some of our learnings and experiences of using Istio at ME Bank. Well, hopefully, I'm actually pretty excited by Istio, and it's actually, I guess it's good to see that everyone else is as well. I sort of try and tell everyone about it at home, and no one really cares. But you know, it's good that I finally get an audience that shares the things that I enjoy as well. Cool. So I guess there's probably not much point. I won't spend too much time on this slide. We've got a fair bit of material to work through. I guess one thing I'll call out: if you do have any questions, maybe just try and hold them to the end. We want to try and get through the content, but we'll have plenty of time for questions at the end. So looking forward to that as well. Okay, so in terms of topics for today, we will, I guess, spend a little bit of time exploring the problem space. We are, I guess, here to explore Istio in the real world, so we need to bring a little bit of the real world into the equation here and explain the problem space we're working in. We'll then spend some time just explaining the overall solution that we're building here, and so that'll help put the use of Istio into context. We'll then walk through a little bit around why we're using Istio, and I guess that'll help understand when you might apply it, when it works well, when it doesn't. I will then attempt to explain how Istio works, so I guess bear with me on that one. A lot of boxes and diagrams and things like that, which is sort of what I do best. When that doesn't work, I'll then hand over to Ben to do a code and demo and actually show you how it really works, which will probably be maybe a little more interesting to many of you. And then we'll finish up with some takeaways. Cool, so this is, if you look at the ME Bank infrastructure and you zoom way out, this is roughly what it looks like. So, if we sort of pick out some of the key components, we have internet banking systems, we have what we call origination systems, so some of the business process workflow type systems used by internal staff, and then we have core systems, so think of those as the mainframes. But in the middle, we have this big box of glue in the middle here, which is the enterprise service bus. And so that's an existing component that's been around for a number of years, and we're looking to replace it. Cool, so just a few stats. So on that bus, there are approximately 250 operations spread across about what we call 150 different services. The majority of those are SOAP-based, and there are approximately 40 batch handlers in there as well. So that's when we're sending basically large batch files between the various systems. That's what it actually looks like. We won't spend too much time exploring this slide, but yeah, there are a lot of moving parts in the bank, but this is sort of, I guess, just give you an understanding of some of the complexity we're dealing with here. So this is, I guess, the equivalent of it's not quite as bad as the Netflix Death Star, but it's our own version of it. So the brief. So when we were asked by ME to provide a new solution, the first, I guess the number one thing was to preserve API compatibility. And the reason for that is that it's a big enough program of work just replacing an ESB platform without trying to change the systems around it. So the first thing we have to do is preserve those existing contracts and try not to break anything. We want to build a platform that's resilient to change. We want to build a platform that, we don't want to build it now and then replace it again in 3 or 4 years' time. We want, a big principle that we're trying to follow is to allow for evolutionary change over time. So we keep making small incremental improvements constantly rather than, big bang migrations. We want to reduce the risk of change. We want to be able to make changes to the existing platform without risk of taking out the entire platform. So we want to make things more loosely coupled, more resilient, and can degrade in better ways. This one over here is probably a little bit, doesn't really mean much, the words, but what we actually mean by that is the current platform is fairly heavily driven by license costs. So if you pay for a platform by CPU cost, you actually end up trying to reduce the number of CPUs you use. You tend to try and put a whole lot of stuff on one box, and that makes it a very tight sort of brittle component. We're trying to break that out, and again, it comes back to that reducing the risk of change. We want to reduce vendor lock-in. We don't want to build yet another proprietary platform. We want to build something that's built on open standards, and that sort of leads into the next thing is that, and as Dave's mentioned at the start, we're trying to build a great team at ME Bank, and a big part of that is using technology that people enjoy working with, and that it's actually productive and an enjoyable experience. So how do we do that? It's easy. We go to the cloud. So the cloud's great because it makes all of your existing problems go away. Tends to bring a few of its own along the way as well, which is unfortunate. But so what we're doing here is taking that big box out of the middle, the existing enterprise service bus, and moving that over here and dropping it into AWS. So that's sort of the outside view of the world, and that's great. That helps us, minimise the impact of change to all the other systems. But it's a big project in its own right. We're moving to AWS for the first time. It is a bank, so we have to, I tread cautiously in that world. So we're moving to AWS for the first time and also moving to Kubernetes for the first time. So there's a lot of work to do here. Let's just peek inside the box. So this will give you a feel for, a lot of these. I'm not going to spend too long on this slide because I guess most of these components are probably familiar to people. We're not here to spend too much time on how to build a Kubernetes stack. But I guess just to call out some of the key components, we have a bunch of Spring Boot microservices. It is SOAP. Java works well for us in this particular environment. We have our observability solution on the left. So that's everything from logging through to time series metrics to distributed tracing. So that's through Elasticsearch, Prometheus, and Jaeger, and so on. And then on the right, we have some of our automation components. And at the moment, we're choosing to use Jenkins for most of that. In the middle, you see some of these little ships flying around here. So these are some of the Istio components, and we'll delve into a little bit of that as we go through. So why did we choose Istio? So we promised we didn't choose it just because it was cool, interesting, and new, Your Honour. But earlier this year, Istio was at 0.5. And it wasn't considered production ready. It was still heavily evolving. There were limited skills and experiences out there. So if you do the famous Stack Overflow search, it's a little bit hard to find answers to the problems we're facing. So not too much copy and paste coding available. But probably a bigger one is that there's sort of not too many case studies out there. And I guess that's part of what we're trying to help with today is to just provide some of it, how we're using it in the hope that other people will reach the same point and start sharing their knowledge with us as well. The other big thing too, though, is that we can't just be too gung-ho about the technologies. We can't sort of put on the cowboy boots and so on and start the big hat and ride in. We're in a bank. We've got to be fairly cautious about the choices we make. So any risks, any technology choices we make have to be the risks have to be mitigated. On the other hand, Istio ticked a lot of boxes for us. So it was actually a really good fit for our requirements. So security, it's a big deal. It's a bank. But if you think about, if we've got, say, 150 different services, that's 150 different endpoints that we have to secure and manage using mutual TLS. And so there's, for any of you that have played with mutual TLS over the years, there's always a lot of work with managing certificates, and anything we can do to reduce that effort is really appreciated. It is a very flexible framework. It is more of a toolkit of things you can assemble, so you've got to be sort of aware of that. There's no sort of it's a bit hard to find these best practices. They might evolve over time, but it is a toolkit, but it is very flexible in how you can configure it. We wanted to build in, obviously we have to build in an available solution. So if this component is right in the middle of the bank, if it goes down, it takes out the entire bank. We've got to make something that's highly reliable. And then Istio provides a lot of out-of-the-box features for things like circuit breakers and rate limiting and so on. And things like rate limiting are great because we can then actually start to, if we build an enormously scalable solution, we might actually then cause problems with some of our companion systems, and we need to make sure we protect them as well. Observability is a big deal. So we need to make sure that when this thing's in production, it's easy to look after, and we can tell when things go wrong, which they do, how to resolve them. And Istio is great because it's got its sort of fingers in every bit of the pie. It actually provides a lot of these hooks out of the box. We've talked a lot about platforms when we're building this solution. So again, 150 different services. We don't want to solve things 150 different times. So we're trying to push as much of the complexity down into what we call the platform layer as possible. And platform is a super overloaded word and means many things to many people. But we've got the AWS platform, but then we've also got our integration platform. And so we're trying to push a lot of that complexity into that, so that when we build services, we're thinking about business functionality. We're also trying to make this thing, we need to pick a maintainable solution as well. And the good thing about Istio, yes, earlier this year it was, I guess still an emerging technology, but it had a lot of big backers. So if you're looking at Google, for example, one of the key sponsors, if you get players like that, we've got some confidence that this is a technology that's going to be around for some time to come. And I think I talked about this earlier, but we wanted something that was resilient to change. So and I'll touch on a little bit more of this later, but we want to be able to support multiple languages and runtimes, different transports and so on, and Istio makes that a little bit easier to manage. So we did look at alternatives, and some of these were alternatives for even during the course of the project. We're not 100% bought into Istio, at least in the early days. We wanted to make sure that we had some sort of parachutes we could jump out. If Istio wasn't working out, we needed plan B. We looked at things like Netflix open source, for example, so Hystrix, Ribbon, Eureka, all those kind of tooling, but it tends to lock us into Java. And Java is actually a really great fit for what we're doing right now. But in a year or two's time, that might be a different case. If we move from building SOAP services to REST or gRPC or whatever the next few years bring us, Java may not be the best answer. And once we start using things like the open source tools there, they become libraries that are embedded in your app. Makes it very hard to switch languages and runtimes. So we wanted to move more to this sidecar pattern, so where we actually offload most of that complexity out to a proxy running alongside our services. And it separates some of these sort of connectivity concerns from the application functionality concerns. So yep, Java now, maybe it's Node.js, maybe it's Golang, and so on tomorrow. It gives us that flexibility. But we have 150 services again, and I keep coming back to that. I'm very repetitive. But managing, we've now just doubled the number of components we have to deploy. Managing 150 sidecars is complicated. We need some way to help manage that complexity, and that's really what Istio brings to the table for us. It lets us do all the things that we can do anyway, but makes it much easier to manage. And I guess just to touch on some of the mitigations, we spent a lot of time monitoring Istio as the project progressed over the last few months. Ben in particular spent a lot of time poring through change logs and pull requests and so on, just to make sure that it's on the right path and to help resolve issues that we were experiencing. We spent a lot of time spiking features. We've also found that Istio is quite again, it's a bit of a toolbox. We tend to just bring in the features that we need over time as we're comfortable introducing them. So what is Istio? So this is more of a deployment view. For anyone that's familiar with Kubernetes, hopefully most of what I'm about to talk about will be somewhat familiar. So we have several different namespaces. So we have tools namespaces containing components like Prometheus and Jaeger. So that's our observability stack. We have most of so Istio, you can sort of think of it as a control plane and a data plane. So the control plane being the things that that manages the runtime, and then the data plane being the part that manages the actual transactional traffic running through your system. So the control plane consists of three major components. So there's the pilot, which is, so whenever you deploy your custom resource definitions that manage, that configure Istio to Kubernetes, it's primarily the pilot that picks that up and pushes it out to the various Envoy proxies running throughout the data plane. The mixer is primarily around observability. So what it will allow us to do is anytime there's time series metrics like Prometheus metrics or distributed trace records picked up from the various Envoy proxies, they get sent via the mixer and then funneled out to your destination of choice. Mixer is also used for some of the real-time policy lookups, such as rate limiting, for example. It maintains some of those counters. The final component, which is actually really hugely useful for us as well, is the Citadel. And what that allows us to do is basically perform mutual TLS within the mesh with pretty much zero configuration. So if you, again, I talk about 150 services a lot, but if you're trying to deploy 150 different SSL certificates and so on over time and managing the expiry of those, it's a huge amount of effort that we didn't want to have to manage. The Citadel rolls certificates, and I wish I could remember the number, but it rolls those every few hours. Within the data plane, we have a sidecar running alongside every one of our services. We also have an ingress controller, which is very similar to like an Istio ingress controller, which is, I guess, similar in concept to the Kubernetes ingress controller, but based on Envoy rather than Nginx or equivalent. We also have an egress controller as well. So all of our inbound traffic and our outbound traffic go via that. And when we talk SSL, we have a single server certificate exposed on the ingress controller, a single client certificate on the egress controller, and then the 150 services then are automatically managed by Citadel. So we sort of manage SSL twice, once on each side, and then the rest of it we can deploy as many services as we like. Okay, this is where it gets hard. So I'm going to try and explain this diagram. So this is really getting into the core of how our solution works. Everything you see here is actually deployed, if I just flick back for a moment, on that ingress controller. So if you look at here, the inbound traffic, we're about to talk ingress routing. This is the configuration that sits on that controller. So we actually go through the gateway twice. So, and I'll explain why in a moment. So we have, there's probably three resources we need to discuss here. So they're Rather than having an ingress resource like you would in a typical Kubernetes environment, we have gateway resources, virtual services, and destination rules. The gateway resource is all about terminating inbound traffic up to the point of sort of OSI level 6. So it's up to the point where you've accepted a TLS connection and verified the client certificates associated with that. The virtual service is all about HTTP routing. So that's mapping path-based rules onto services, onto destinations. And then the destination rule is about how you make that connection onto the next hop. So if you look here, we've got a single host name, and again, we don't want to make changes to external systems, so they all think of the ESB as a single monolithic platform. We expose a single host name, and in this example, we've got like a test environment, a test integration environment at ME Bank. And we're using ME issued certificates, so out of their internal CA. We then map those, we have path-based routing, so we use, every service has an individual path that then maps onto an internal host name that's managed within the mesh, because Istio really likes to work with hosts rather than paths. Then once we get to the destination rule, we're now working with mutual TLS, and that just describes how to hit the next hop. That will then map onto a particular specific service name. We then have wildcard service entry on the gateway again, so we've actually now made a loopback connection. And if you're worried about performance of that, I guess it's a concern, but it is literally a loopback connection on the network, so there's not too much additional overhead. The latency is fairly minimal. We then have a virtual service entry per destination service that we want to expose. And a big reason for doing this separation is managing complexity, and again, minimising that risk of change in production. So our virtual service is a fairly static thing. We define that once. We define out our list of 150 services. That rarely changes. We can then manage the configuration of each of those virtual services. And this will contain things like Canary deployments and which versions to target and so on. That changes quite regularly as we're doing deployments. But we know that when we make a change to that, we're only risking a deployment for one service. Again, that maps onto a destination rule, and then we make the hop on to the actual service of choice. Okay, Canary deployments. This one's probably a little bit more of an advanced case. I'm just going to have a little drink of water here because I get nervous when I talk. Okay, so the last one I showed two services. In this case, we're just really talking about Canary deployments for a single service. And just to make it a little bit more advanced, we're actually going to do two loopbacks through the gateway here. So the first case is, and this is sort of, I guess, that pluggable nature of Istio. It's very easy to keep adding on to the solution as you go, which is quite nice, quite flexible. So we have an inbound service, same entry, same virtual service mapping, same destination rule, maps through to the gateway. At this point, the service entry, we have a virtual service, but it now has a number of different matching rules. So just ignore this one for a second. This is typical Canary deployments in Istio. So Istio provides a fairly flexible out-of-the-box ability to do Canary deployments. You can use a number of different ways of matching those deployments to various service versions. And the typical one will just be a basic weighting, send 10% of traffic to the new version, 90% to the old. But in our case, we're not Facebook. We can't just randomly pick users and throw some random stuff at them and see if it works. We do have to pick pilot user groups and selectively pick those. So what we actually do is and I guess the problem we have there is that we have to start looking at the payload to figure out who the user is. We've got SOAP services. The user that we're acting on is buried inside a SOAP payload, and Istio can't unpack that itself. So what we do is, the first time we come through, we have a match entry that says, hey, we don't know who the user is yet. We actually route it onto a custom component called our content lifter. And that is the thing, we'll unpack the SOAP payload, pull out the particular username or account name or whatever we're trying to pilot, lift that up into a header, and route that back through to the gateway again. And at the second time through, we can then start to have matching rules that match on those headers and then route to the appropriate version. The other piece that we have in here is a thing called subsets, and this is just something that I'll just mention because Ben will touch on it more later. Subsets allow us to pick specific labelled versions of a service on the mesh. Finally, egress. So egress, the extra, is another resource we need to introduce, which is a service entry. So anytime we're talking to something outside the mesh, we need to register those endpoints within Istio, and a service entry is a mechanism to do that. So we have a service running up here, along with its sidecar. Assume there's a sidecar with that. It makes a connection out to, so let's say, service A.on-prem at ME. We will then have matching rules in a single virtual service entry that basically determine where the traffic is originating from. And because we don't want the traffic to go direct from the service's sidecar outbound, in fact we can't, we actually put Kubernetes network policies to prevent that from happening. We actually force it to go through this egress gateway, which is controlled in a different way. And so we have a matching entry. The first time you hit it, it matches and says, okay, it's come from a mesh sidecar. We will now send the destination back to the egress gateway now. So the egress gateway now has it will now receive that request. And when it makes a connection outbound, it looks up the virtual service entry. These little green lines are configuration linkages, they're not connections. It will look up that entry and will determine that now, okay, in this case, we're allowed to go directly to that point. We go out through our destination rule. We're now using ME client certificates to make that connection. We look up the service entry and know how to make that connection out to the target endpoint. I hope that makes sense. Cool. If it doesn't, we've got someone else on hand, so Ben will actually show you how it really works.
Okay, so could I just get a show of hands of who's actually used Istio before, like just even the most basic demo? Okay, so a decent number of people starting to get familiar with it. Cool. So what we're going to do is we're going to try and run through a really basic Canary demo, showcasing how easy it is to really enable that kind of Canary capability that typically would be quite hard to do in a more traditional kind of infrastructure model. So the first thing before we start is to kind of run through what some of these policies actually look like that Brett kind of gave a really top level overview of. So what we have here is what a destination rule actually looks like. So to first start off is in 0.8 of Istio, they released a new mesh API of representing the overall mesh topology. And so what that effectively has introduced is a new set of CRDs. So custom resource definitions are the ways you represent a more bespoke way of interacting with Kubernetes. And so what at the end of the day Istio is doing is consuming these CRDs and translating that into policy that exists within the control plane as well as the sidecar envoy proxies. So what we have here is for the first CRD is the destination rule. So what we do with the destination rule is we specify a host name which must be resolvable within the Kubernetes environment. So what we have here is a small microservice that I've deployed as part of this demo. And so we can see here that we're looking at demo microservice that's living in the deployment namespace, and that effectively has been constructed because I've defined a service entry within Kubernetes. So now this is now resolvable within the Kubernetes mesh. And so next, Brett mentioned how easy it is to do mutual authentication between services within your Kubernetes cluster or within your Istio service mesh. And so in order to enable mutual authentication, in order to reach this destination up here, we just specify this little block of YAML here. We say that in order to establish the connection to demo-microservice, we just say that we want to use Istio mutual. And what this will do is it will translate into Envoy using mutual authentication to communicate with that defined endpoint within Kubernetes. Now, what we also have is, as Brett mentioned, the construct of subsets. So with a typical service definition within Kubernetes, you can specify selectors. So selectors say what you want to filter on in order to create effectively an IP to load balance on to a given number of back-end pods. So what selectors, what subsets are doing are applying that same kind of filtering capability, but now on pod labels instead of selectors. So if you can imagine that I've deployed 2 microservices, version 1 and version 2, and I've just put a label on that pod spec that says this one is version 1 and another one is version 2. So that's what this is here. We've got version 1, so I've labeled a key value pair on that pod spec of version 1 and another one with version 2. So now if we run through another custom resource definition that was introduced in 0.8, we've got a virtual service. So what a virtual service does in terms of how the network request is handled or the HTTP request is handled, it handles the overall routing of a request. So a request will come into the service mesh and the virtual service will be responsible for determining which destination to send that traffic to based off a set of matches or criteria that you can specify. So for example, you could say that if a request comes in for a certain URL, then you'll route it to a given service. Or you can even go more kind of detail or granular with that request, and you can say if a request comes in with a certain header, you can send that to a different backend or a different version. So jump into that, it's just another virtual service, but the difference between a virtual service and a destination rule is that we can specify where we want this configuration to live within the service mesh. So for example, you can have the configuration for the virtual service living just on a given gateway, or an ingress gateway or an egress gateway, or rather an ingress or egress gateway. Or alternatively, there's also a predefined name here where you can see mesh. So what mesh represents is effectively deploying this configuration on every single sidecar in the service mesh. So every single sidecar that lives alongside every pod that you're deploying within your Kubernetes environment. So what we're doing here is we're deploying this virtual service on not only the ingress gateway, but also on the sidecar that's accompanying each of the microservices I've deployed. So what we do here is we specify that when a request comes into the ingress gateway on this domain, then this is the virtual service, the one that I've defined here, this overall definition, is what's going to take that request and then apply certain rules on how to determine where to send that in terms of a destination. So next we have a destination, and what this effectively is resolving to is a destination rule behind the scenes. So we're just saying that if a request comes in for this domain, then send it to this destination, which is effectively the same. And we're saying here, or we're referencing a subset. So this is where we're able to say if the request is coming for this domain, then we want to send all requests to the subset v1, which is effectively going to be all the pods with that label. Finally, we then specify the weighting we want for that destination. So in this case here, I'm just doing effectively 100% of the traffic to version 1. So what I've got here is a small little demo, which is just a little client application that's going to be making requests to effectively the Istio service mesh that I'm running on my MacBook here. So what I'm just going to show you here is proving that it is making requests to a backend. So if I hit refresh here, we can see that it's making 25 subsequent requests to the backend that I'm hosting on my laptop. And what it's doing, if we click on one of these requests, is it's just serving a color. So in this case, it's blue, and it's serving me the version. So what I'm doing in the client side is using that to create this nice little application. So what we're going to do is we're going to kick off and show a little Canary deployment. So we're going to introduce 10% of the traffic is now going to be routed to version 2. So if we jump over here, and let me just kick off some background traffic as well here for the later part of the demo. So if I now come over here, I go make Canary. What this is going to do is it's going to deploy effectively another virtual service definition. So if we just look what's inside that. So what we're doing here is we're just saying route 90% of the traffic to version 1 and 10% of the traffic now to version 2. So just to go over that, if I now refresh a couple of times, we can see now we're introducing 10% traffic and the client-side application is now receiving that. So there's obviously a certain degree of randomness or heuristics around how that load balancing occurs. So you can see here I made a random request and we got a little bit more than 10%. But if I keep making requests, overall it'll converge to being roughly 10% on average. So if we actually just jump into looking at what some of that policy actually looks like for implementing a Canary deployment, we can see here that we're using the same virtual service custom resource definition, but we're also deploying on the demo and the mesh, but this time we're actually specifying a little bit more information about how we want to distribute traffic once it comes in on that destination, on this hostname. So here we're saying we want to send 100% of the traffic, 90% of the traffic to V1, and we're sending 10% of the traffic to V2. So now what I've sneakily done is I've introduced effectively what you'd call a bad release candidate. So the application that is V2, I've introduced some anomalous latency. So what I'm going to show here is how we can go about effectively doing some root cause analysis or evaluating the overall health or performance of that release candidate before then potentially rolling out more traffic to it or potentially working out whether we need to roll back to the previous version. So what I'm showing here is Jaeger. Now Jaeger is the distributed tracing, is a nice little distributed tracing UI that can consume from Elasticsearch as well as Cassandra to produce a nice view of the traces. So as I showed here, I'm generating some traffic in this window over here. And so what we should see here in this view is if I hit refresh here, we should see these traces coming in. Now, as I mentioned before, I've introduced a poor release candidate, and we can already see that in this trace here. We can see that overall, most of these requests that are coming into Istio are pretty low latency, but we see this anomalously high group over here. So if we click on that and we deep dive into that actual trace, so this is effectively distributed tracing in a nutshell, we can look in here and we can see information about the actual pod that handled that request. So in this scenario here, we can see that V2 handled that request. And so you could imagine a scenario where we could now go, this is a poor release candidate. We're seeing anomalously high latency spikes with it. And you could then look at what the change request was and go back to the developer and hypothetically tell them to refactor their code or make the necessary improvements. So some of the other tooling we've got as well is we've got Grafana. So if we just jump into this and have a look at a quick view of, say, the mesh overview. So we can also see here in the metrics coming, we're handling 24 operations a second, which is the load coming in on this little siege request that I've kicked off. And we can see here that immediately we can see this anomalously high P99 latency. So we can see that on average we're seeing roughly 400 milliseconds of requests, and we can see that that's on V2 of the application that I've deployed. So this is just another tool we can use that's part of our toolbox that we can use to kind of debug the performance of a given release candidate within Istio. And again, the reason why we've got these metrics is because they're being shipped out of the box with a sidecar in place. So we don't have to do any instrumentation of our microservices. This just comes out of the box, and it allows you to minimize the amount of work you have to do to get this kind of analytics. So Mixer is responsible for the aggregation of all of these metrics as well as the spans. And then finally, what we're also going to show is a new tool that's coming out as well, that's gaining a little bit more traction, which is Kiali. So I believe this is coming out of Red Hat. And this is just another way of visualizing the topology of your service mesh. So if we add traffic animation here, and if we add, say, response time, what we can see here is a kind of real-time view of how traffic's actually flowing. So what Brett mentioned earlier is we do this loopback type mechanism here in order to translate a front-end URL into back-end URLs. So you can see here that we can see the traffic coming in, it does the loopback, and then after the loopback's taken place, Istio works out which service it needs to send it to. So for example, in this case here, it's sending it to V1 and V2. And in this topology view, we can also see that V2 has this anomalously high latency in this nice little topology view. So you can imagine when you're running a large number of services, how complex it might become to trace and track how everything's working together and how you can go about debugging or carrying out root cause analysis of the services that are being deployed in a potentially continuous deployment manner. So you've got very high frequency deployments occurring within the service mesh. So it's this kind of group of tooling that's now available because of that sidecar pattern that we're able to very easily trace and track and alert on anomalies that are occurring within deployments. And what I'll show you next is how easy it is to now roll those malicious or unexpected changes that have been deployed into the mesh, how easily we can roll them back. So if I go back here, what I'm going to do is I'm literally just going to apply that policy back, the first one I had in place. So I've just got some make files here that are wrapping these commands. So now, before I had a couple of little red V2s in my application. So if I now go to the application and I hit refresh, we can see that there's no more red. So if I just prove to you that I'm not faking this, if we go over to network and I hit refresh, so we're making requests to the backend and we're seeing no more V2. So that malicious change or that bad change has now been rolled back, and we're ready to kind of keep the services fully operational. So that's it from me. Handing it back to Brett.
Right, cool. Thank you, Ben, for showing. Yeah, that's a little more detailed than I can take it, so that's great. Cool. So I sort of hope today, it's a little bit hard to pick out exactly what we should show you. We sort of want to pick a bit of a mix of some of the concepts as well as some real code as well. So I hope you found it useful. I guess just want to leave you with a few takeaways. So we think Istio is ready. I think it's really made our solution far more flexible, far more mature. We've been able to introduce a lot of capabilities that we just wouldn't have been able to do without Istio. But I guess that it is worth calling out that Istio is not simple. So it's a little bit like Kubernetes itself. If you've only got a couple of a simple application to deploy, it's probably a little hard to justify. You don't really spin up a whole cluster to deploy 2 containers. It's overkill. But on the other hand, if you've got a large distributed suite of services and applications, then it starts to make sense. And Istio is similar to that. If we had 2 or 3 endpoints to manage, we just bundle that functionality straight into the service. Whereas when we've got hundreds, well, it would be hard to imagine doing it without Istio. Just the thought of managing hundreds and hundreds of SSL certificates just is horrifying. So in terms of what the crossover point is, how many services do you need or how many endpoints do you want to be protecting before Istio is useful? Well, I don't really know. It's hard to give an exact answer there, but what I am pretty confident about is that number will reduce over time. So as we start talking about managed Istio with Google and so on, I think it'll become easier, and we'll see more and more tooling starting to build on top of it. So yes, we're pretty happy with the solution we've come up with. We think it's something that's pretty resilient to change. We hope it's something we can continue building on as we go forward. A little bit hard to cover too much today, but if you'd like to know more, please have a chat. The demo that Ben has put together is available on GitHub, so feel free to download and have a play. Raise PRs, spam us, raise issues, whatever you'd like to do there. And finally, feel free to reach out and have a chat. Cool, thank you very much.